So at this point, let's try to investigate the relation between the max terms and the min terms. So the claim is this: max term and min term with the same index holds the complement relation. What I mean is M3, capital M3, has a relation with capital small m3 as an inverse relation. So max term 3 equals inverse of min term 3. We can easily prove it. Max term 3 is your x or y bar or z bar, right? And that's by De Morgan law, it's x bar y z bar, and x bar y z bar, sorry, by De Morgan law it is x bar y z whole bar, and then x bar y z by min term definition it is m3. So that means your max term 3 is equal to inverse of min term 3. Now let's think a function f x y z, if it is sigma of 0 to 5 7, then inverse function of that, inverse function we already did cover that inverse function, or I think we called it complement of a function. Remember we had this discussion, dual of a function and complement of a function. So complement of that function would be actually your sigma of m1346. So in general, if a function is a sum of couple of min terms, like a min terms a set of min terms, if a function is summation of set of min terms, then its complement function would be sum of the rest of the set of the min terms. Just to elaborate on this idea, so with a 3 variable like f x y z, we have like total 8 min terms, right? m0, m1, m2, m3, m4, m5, m6, m7. Then if your function is sigma of m0 to 5 7, so that's a set of min term, then complement of this same function would be basically you collect all other rest of the min term set, and that becomes your complement function for the given function, right? So in this way, with that explanation, your f bar xyz is sigma of m1346. So if xyz, we can write it down as your m1 or m3 or m4 and m6 complement. Just make that complement term, like we complement both sides in this claim, like f bar xyz equals sigma m1346. We complement both sides, then we get f xyz as m1 or m3 or m5 or m6 whole bar, which means by De Morgan we can write down it as m1 bar dot m3 bar dot m4 bar dot m6 bar, and with the previous relation, m1 bar is basically your capital M1, right? This min term 1 bar is max term 1, min term 3 bar is max term 3. Likewise, we can then write f xyz is basically your product of the max term 1 3 4 6. That means your SOP expression is equivalent to its POS expression, like with exact set of disjoint indices of its SOP equivalent. So if my SOP was sigma m0 to 5 7 in this example, then I can express the same function as a product of sum with those max term whose indices are completely disjoint set to what the original SOP had. So with this discussion, what we are trying to conclude here SOP and POS are not kind of two different concepts. They are kind of two different views of the same Boolean function. So, if we kind of limit our discussion with respect to SOP, sum of product term, we do not have to worry about POS and what happens there, because they are kind of equivalent. POS and SOP are equivalent, as we are proving in this slide. So what we'll do with the rest of the discussion, we'll stick to SOP, sum of product, okay? Because product of sum is basically equivalent to sum of product. So that's the conclusion we are trying to make in this slide.